Good morning. Today is April 2. This is CS 746. Today's lecture on classification. This is part 2. So today we are going to discuss about a few methods in classification or a few models in classification. So classical machine learning. So as we said previously, it was divided into supervised and unsupervised learning. Supervised means we know the labels, and unsupervised means we do not know the labels and we want to classify things. So supervised, in supervised, we have classification and regression. So we have covered classification in this class. So we are going to see that, sorry, we have covered regression in this class. So we're going to see the classification for one more lecture. So this is the second lecture, I guess. And these are about unsupervised learnings, clustering, dimensionality reduction, association, analysis, and so on. So there is a little picture here. So in 2011, when someone learned about machine learning, so they could be like, oh, I can predict stock market, so I'm going to be rich. But when coming to 2018, when models are getting popular and so on, and they were like, is the model really giving me the results? So they were like that. So the data is becoming like not too much good, but yeah, so there are a lot of differences between the models they have created those days and we're creating these days. Yeah, there are differences. So this is raw data and this is labeled data. So we have labeled this right here like greens and lavender, and overfitting would be something like this. So is this supposed to be jokes? So what is classification? Classification is a form of pattern recognition. So the classification algorithm applied to the training data finds the same patterns in future data. So we will give you the model some input variables like these, and that is supposed to be categorized like this. So for example, if we have like veggies, so the classification algorithm is doing veggies together and the other stuff here together, the ice creams and other stuff together. So this is what a classification should do. So a classification should classify things based on the input data. So we train the model to do that, and that needs to be done on the testing data set as well. So on the unseen data as well, that should perform. So this is classification. So this is also supposed to be a joke. So these are the male before married and after married, and this is the female before married. Sorry, this is the male, this is the female. He said, professor said, it's just a joke if you understand. So today's topics. So we're going to discuss about logistic regression, naive Bayes, KNN, and SVM classifier. I guess we have like 67 slides, so I'll just go through it quickly. So logistic regression, this is something similar to the regression we have seen, like the regression line, but this is S-shaped curve. And naive Bayes is something that is related to the probabilities. So we are going to see the prior probabilities and posterior probabilities and define the classifier. So that's something related to naive Bayes. And KNN. So this is supposed to be K nearest neighbor classifier. So we classify a data point where, I mean, if the surrounding data points are classified as 1, so that's going to be classified as 1. If it's going to be classified as 0, the nearest neighbors, it's going to be classified as 0. So we're going to see. And SVM classifier is something which is much more useful than any of these, because we could classify the SVM in not just using linear lines, but we could classify it, something like circles or parabola or anything. So we are going to see those with examples. So first, let's go through logistic regression. So this is the S curve for the logistic regression. So it simply classifies a given point into 1 or 0. So we have a multi-class classification as well, but that is not discussed in this class. But a simple logistic regression is classified into either 0 or 1. So that's the use of logistic regression. So it classifies an element. So it logistic regression is a classification algorithm. It is used to predict a binary outcome, 1 or 0, yes, no, true, false, anything. So given a set of independent variables. To represent a binary or categorical outcomes, we use dummy variables. So you can also think of logistic regression as a special case of linear algorithm. So because it's again a line right here, the straight line, but there are curves to make it or to classify it into zeros or ones, where all the data points will be classified as 0 or 1 right there. So in simple words, it could predict a probability of occurrence of an event by fitting data into logic function. So this is what a linear regression looks like. And a logistic regression would be like this, as shown here. So all these bottom points are classified as 0 and this as 1. So predicted y lengths within 0 and 1 range. So if you look at the differences, linear regression, as we know, it predicts the outcomes. It's just not classified. It predicts the continuous dependent variables. So logistic regression is used to predict the categorical dependent variables. I mean, it categorizes and it predicts. So linear regression is used to solve regression problems, and logistic regression is used to solve classification problems. So in linear regression, we predict the value of continuous variable. In logistic regression, we predict the values of categorical variables. So in linear regression, we find the best fit line by which we can easily predict the output. And here we have the S curve as shown earlier. And here least square estimates, so nothing but the difference between predicted and the original data point. So that is what used to estimate the accuracy, something like mean square error or mean absolute error like that. But in logistic regression, we use accuracy. So we'll see how many data points are classified correctly. So that's what the accuracy means. So the output of linear regression must be continuous value, such as price, age, etc. But the logistic regression is something categorical. So it categorizes into 0 or 1 or true or false. So in linear regression, it requires that relationship between dependent and independent must be linear. But in logistic regression, it is not required to be linear, because we are not making a linear line. So we are just making a line to separate these two things. So it's not always required to be linear. So in linear regression, there may be collinearity between the independent variables. In logistic regressions, there should not be collinearity. So this is one point to be remembered. So collinearity is nothing but having a correlation between the independent variables. So that shouldn't be there in logistic regression. So logistic regression is a part of large scale of algorithms known as generalized linear model. So in 1922, so these guys proposed this model with an effort to provide a means of using linear regression to the problems where we could directly suit it for applications of linear regression. So something you might be interested to read. So assumptions, this is again an important part. So dependent variables must be categorical in nature. So that's the purpose of logistic regression, right? We need to categorize. So this is an assumption that dependent variable, that is y variable, should be categorical in nature, and independent variable should not have the multicollinearity. And GLM does not assume a linear relationship between, there is no need or not a necessity to have a linear relationship between dependent and independent variables, because we are not doing regression here. However, it assumes a linear relationship between link function and independent variables in logic model. We'll see what is a link function. The dependent variable need to be normally distributed. So it's an assumption that dependent variable should be normally distributed. It does not use OLS, like as we discussed earlier for linear regression, but it uses MLE, maximum likelihood estimation. So errors need to be independent, but not normally distributed. So sigmoid function. So we use sigmoid function to classify things, because sigmoid function can be either categorized to 0 or 1. So sigmoid function is a mathematical function used to map the predicted values to probabilities. It maps any real values into another value ranging from 0 to 1. So the value of logistic regression must be between 0 and 1. which cannot go beyond this limit. So it forms a S curve. The S curve is called a sigmoid function or a logic function. In logistic regression, we use the concept of threshold values, which defines the probability of either 0 or 1 such a value above the threshold. So if we take an S curve, so not all values fall into 0 or 1. We will have a threshold where we say that, for example, if we take 0.5 as a threshold, we say if the dependent variable is above 0.5, that should be categorized as 1. If not, it should be 0. So we will be having a threshold to define or to categorize a data point into 0 or 1, or either true or false. So this is logistic equation. So if we think about, for example, threshold, this should be somewhere around here. So if you check here, there is a small line, so that should be a threshold. So the points falling below that line will be categorized as 0, and the points or the data points falling above that line will be categorized as 1. So this is about threshold. So this is the logistic model. So this is the linear model. So this is something, the blue line is defined with mx plus c or b1x plus b0. So this is the linear model, and the logistic model is something like 1 by plus e power minus the linear function. So that's giving us the S curve. So the odds ratio is by computing P. So this is something, the definition of odds ratio, P by 1 by P, sorry, 1 minus P. And this is the logic function that defines this thing. And the coefficients of B1 is the amount of logic changes with 1 unit change in X. So that is one thing. So pros and cons, logistic regression is simple, giving probabilistic outputs. So it gives the likelihood of an event falling into 1 or 0. So we are defining it threshold and making it to fall into a category. So it gives the probabilistic output. So feature, importance, and directions. And cons are like assumption of linearity in the logic can rarely hold. So not always the dependent and the independent variable should be in linearity. So uncertainty in feature importance, not robust to big influentials. So yes, not robust to big. Naive-Bayes classifier is one of the classifier we are using today. So it's gaining popular lately. So when we think about neural networks, so Bayesian neural networks is one of the most widely used neural network in the medical field, because it gives the probabilistic results rather than just classifying it. It just says, instead of saying this person has some kind of disease, it says this person has the probability of having this disease. So that's something important in medical field, and that's why naive Bayesian neural network is gaining some importance, and this is about the classification. So it's naive-Bayes classification. So it again depends on the probability. So prior and posterior probability. So while we may not realize this, this is the algorithm that's most commonly used to shift through spam emails as well. And it applies what is known as posterior probability using Bayes theorem to do the categorization on the unstructured data. And in doing so, it make a naive assumption that the predictors are independent, which may not be true. The model works well with a small training set, provided all the classes of the categorical predictor are present. So let's see what all these about. So this is the naive Bayes. So probability of A given B is equals probability of B given A times probability of A by probability of B. So probability of A given B is called posterior probability, and this is called a likelihood, and this is the probability of A, and this is the probability of B. So in classification technique, based on Bayes theorem with an assumption of independence among predictors, in simple terms, a naive Bayes classifier assumes that the presence of the particular feature in a class is unrelated to presence of other features. For example, food may be considered. Let's just skip this. Let's have a training data set of weather and corresponds target variable play. So basically how we build this naive Bayes. So first, before looking at the data, we make our assumptions. So that's called prior probability. And after seeing the data, we'll have posterior probability. So what that means, So for example, before classifying anything or before giving anything to the model, the data to the model, we'll define prior probability. We say that these variables are most important for classification. So we'll say that, but we'll also say at what confidence intervals or what standard deviation is that important. So that's called prior probability. We'll define the probability. We'll say that these variables are most important to classify. I am thinking these variables are most important, and then we'll say at what confidence it's important, and then the model see the data, and then it gives based on our prior probability. It again derives the posterior probability. I mean, we could say in the posterior probability that you could go or you could assign weights to these variables at this standard deviation and something like that. So that's how basically Bayes algorithm works. So step one is to convert the data set into a frequency table. So here is the problem. So data set of weather and corresponding target variable play. Now we need to classify whether players will play or not based on weather conditions. Let's follow the below steps to perform it. So we have some table giving weather, and in that whether the players will play or not. So we have some table defined like that. So what are the steps we need to follow? First, we'll classify them into frequency table, and then we'll create a likelihood table by finding the probabilities. And then now we use naive Bayes equation to calculate the posterior probability of each class. The class with the highest posterior probability is the outcome of prediction. Let's see. So this is the table we have. So on the sunny day, they haven't played. On overcast, they played. On rainy, they played, and so on and so forth. We'll just create a frequency table. So S and Nos for sunny, overcast, and rainy. Overcast, rainy, and we'll have a grand total. So this should be the number of data points we have here. And likelihood table is something like how likely they would play on a overcast condition. So that's S is 4 by total 14, 0.29. And on rainy day, S is 2 and no is 3. So the total likelihood would be on rainy day, it would be 5 by 14 and so on. And how many times they played? 9 by 14. So this could be used somewhere like this. So what is the probability of them playing given sunny? So an event occurring given other event. So they are playing given sunny. So this is the formula we discussed. And P of sunny, yes, that would be 3 by 9. So this is sunny and this is S. So this should be 3 by the total 9. And P of sunny, probability of having sunny days would be 0.36 and probability of having yes would be 0.64. So we compute the formula using these equations. So we create a likelihood table and we know this formula and we apply this formula using the table we have. So it's simple. So naive Bayes uses a similar method to predict the probabilities of different classes on various attributes. We discussed this, and the algorithm is mostly used in text classification and with problems having multiple classes. So not just to classify into one category, but we could also classify them into multiple categories. So we classify them into a category if that has a better probability than classifying into other classes. So types of naive Bayes, we have multiple types of naive Bayes models: Gaussian, multi-model, multinomial, and Bernoulli. Gaussian is something like normal distribution. So Gaussian noise is nothing but normal distributed. So we have a normal distributed curve here. This means if predictors takes continuous variable values instead of discrete, then the model assumes that these values are sampled from a Gaussian distribution. And multinomial is something, again, a naive Bayes classifier when the data is multinomial distributed. So it is primarily used for document classification problems. For example, if we need to categorize a document into sport or politics or education, so we then use multinomial classification because we have multiple classes here. And Bernoulli is something similar to multinomial. The predictor variables are the independent Boolean variables, such as if particular word is present or not in the document. So this is about the types of naive Bayes, and we also have, I guess, applications. Real-time predictions, yes, naive Bayes is useful for real-time applications. And multi-class predictions, yes, it could be used for multiple classes or to categorize into multiple classes. Text classification is spam filtering, sentiment analysis. We have discussed about these things, and recommendation systems. So something like whether you will get an admission in this university or not. So this is something where Bayes algorithm is also widely used. So it gives us the probability, not only just classifying, but it says like you have this much chance to get into this university, and so on. In Naive pros and cons, it is easy and fast to predict class of test dataset. It also performs well in multi-class predictions, so that's a pro. When assumption of independence holds, naive classifier performs better compared to other models, and it performs well in case of categorical input variables. For numeric variables, normal distribution is assumed, and it could also be used for categorical input variables to classify the output as well. So cons is something like if categorical variable has a category which was not observed in training data set, so probability will be unable to make a prediction. So if categorical variable has a category, yes, which was not observed in training data set, yes. So while training the model, if we haven't, so if our class is highly imbalanced, and if we are trying to make it to training and testing data sets randomly, then there is a high chance that one of the class may be missed in training data set. So in that cases, our model will not predict the class that was missed in the training data set correctly. So it's also important for us to classify or to make into training and testing data sets in such a way that every data set has all the classes in it. So that was one of the important things. And our model could not predict well if we miss out or if we have very low classes categorized in our training data set. So this is one of the con. On the other side, naive Bayes is also known as bad estimator. So the probability outputs from predict proba are not to be taken too seriously. So this is a function. Another limitation of naive Bayes is the assumption of independent predictors. In real life, it is almost impossible that we get a set of predictors which are completely independent. And so this relies mostly on independent input variables, but in real life, so it's very difficult to get such independent variables. So somehow the independent variables would be related to each other. Next would be KNN. So K nearest neighbor classification. So it's simple. So we have these green dots here. We have these red dots here. So if we place a new data point here, so where does this new data point classify in? Either red or green. So it calculates the nearest neighbors. So if it's like 3 nearest neighbors, so it calculates the distance between the new data point and the red one, the new data point and the green one. So it just takes the nearest 3 points and calculate the distance, and it will categorize into the distance that is shorter. So here, so that's what happening here. Just initial, this is the initial data. It calculates the distances between the nearest values, nearest 3 values, and it's just categorizing whichever is having the short distance. So that's KNN. So that predicts based on the specified number k. So here, since k is 3, it's just taking the nearest 3 data points and computing their distances. But if it's 4, then it takes the 4 data points from each of the class and computes the distance. And again, taking 4 will make it into another classification. Making 3 will classify it into another classification. So that's why k, defining k is most important in KNN. That's the most important hyperparameter whenever you're using KNN classification. Here, the pre-processing of the data is significant as it impacts the distance measurement directly. Unlike others, the model does not have a mathematical formula, neither any descriptive ability. So it rather than depending mostly on mathematics, it just depends on the algorithm we provide that's taking the nearest distance and classifying it into that category. So here parameter k needs to be chosen wisely, as the value lower than optimal may lead to higher value impedance prediction accuracy. It is a simple, fairly accurate model. And KNN is one of the simplest ML algorithm based on supervised learning techniques. KNN algorithm assumes the similarity between new cases and available cases and put the new cases into the category that is more similar to the available categories. So KNN algorithm stores all the available data and classifies a new data point based on the similarities. So that's what we discussed earlier. And KNN algorithm can be used for regression as well as for classification, but mostly it is used for classification tasks. So KNN algorithm can be used for regression as well. KNN is non-parametric algorithm, which means it does not make any assumptions on underlying data. So it doesn't depend on the data. It just depends on the distances between the nearest neighbors. So KNN algorithm at the training phase just stores the data sets. And when it gets new data, then it classifies the data into the categories that is much similar to the new data. So there's nothing for the KNN to do in training phase because it does not rely on data. So it's not learning any patterns inside the data, but it's classifying the data which has the least distance between the two categories. So in training phase, it just stores the data rather than learning the data. So it again, we have various graphs to see the optimal value of K. For example, we have elbow curve where we'll take the least point of the K to make good predictions and so on. So here we use graphs to make optimal or to choose optimal K value, but there is nothing like training phase for KNN. So for example, suppose we have an image of creature that looks similar to cat and a dog, but we want to know either it is cat or dog. So for this classification, we use KNN algorithm. It used on the similarity measure. So KNN model will find the similar features of the new data, set it to cat or dog images, and based on the most similar features, it will put into either cat or dog. So it counts on the features, and if it finds the most wherever it finds the more number of features, it just categorizes into that category. So here we have why do we need a KNN algorithm? Suppose there are two categories, A and B, and we have a new data point here. So to solve this type of problem, we need a KNN. So whether this new data point will categorize into A or B. So looking at the data, we just can't categorize these data points, but using KNN, we could. So based on the K value, we'll take the nearest neighbors and then compute the distances. And then whichever is the least distance will be classified into that category. It's fairly easy and straight. So step one, select the number of Ks and calculate the Euclidean distance. Take the K nearest neighbors as per the calculated Euclidean distance. So among these K neighbors, count the number of data points in each category. Assign the new data points accordingly. Our model is ready. So that's what we discussed till now. So it just chooses to the it just goes to the category which it has the least distance. Suppose we have a new data point and we need to put it in a required category. We have the K equal to 5. So it just computes the nearest 5 values from each of the category. And then whichever gives it the least distance will go into that category. So Euclidean distance. So it's simple. X2 minus x1 whole square plus y2 minus y1 whole squared root over. So that's the Euclidean distance. It's easy. So that's Euclidean distance is a distance between two data points. The Euclidean distance, which we have already studied in geometry, is probably is the first formula we would have learned to calculate the distance. By calculating the Euclidean distance, we got the nearest neighbors as 3 nearest neighbors in category A and 3 nearest neighbors in category B. New data points must belong to category A because it maybe it is the closest to this one. So how to select optimal K? So we have various methods to select the optimal value. So there is no particular way to determine the best value of K. So we need to try some values to find the best out of them. So preferred value of K is 5, but it's not always optimal. Very low values can be noisy and lead to the and can be affected with the outliers in the data. And large values are good, but it might find some difficulties to categorize as well. So for choosing the k values, we use error curves or k values with optimal variance and bias error is chosen as k value for prediction purposes. So we have some curves like this. So we have plotted error rate and we have plotted k value right there. So we need to find a value with least error rate and least k value. Again, it depends on the individual to choose the best value. Basically, the error rate and k value would be somewhere like these curves. It's not the correct curve that was taken for the example, but it so it's called elbow curve. The curve should be somewhere like this, and we'll find a value where the least error rate and least k value meet. So again, different perspectives from different persons may choose different k values, and again, it depends on the individual. So some may think it should be the optimal value because it has least error rates and even least k value, and some may think this one because it may increase some k value, but we're getting least errors. So it again depends on the data you're using, and it again depends on the individuals that is using to make the decision on k value. So required data pre-processing, data scaling. We need to bring every data point into a single scale. That's a common pre-processing technique used for any of these models, dimensionality reductions. So KNN may not work well if there are too many features. So we'll reduce the dimensions. There are dimensionality reduction techniques as well, or we could just drop some of the features which might not be more uh, related to each other, or missing value treatments. So if one out of the M features, one feature data is missing for particular example training, then we cannot locate calculate distance from that point. So it's again important thing to note. In pros and cons, it's simple. It is robust to noise, and it can be more effective in the training data. So always need to determine the value of k, which may be complex sometimes. So it's not always an easy task to find the k value from the data set. So we need to think about it. We need to have subject matter experts sometimes to choose the value of x, because we do not know whether classifying one thing into other uh, mistakenly may lead to higher changes in the output, or sometimes it's okay to classify one or two data points. So in that time, we'll take more x and less error. And in the first case, we'll take very less error and more k. So that's one thing. And again, the complexity of the model increases with the increase in k value, because we need to compute those many distances. So this computation cost is high because of calculating the distance between data. Oh, that's what the given in cons. So SVM. So I guess this should be our last classification technique today. So SVM is again one of the popular classification techniques we are using till date, because it can be classified based on the parabola sometimes, and based on the circle and anything. So SVM. So this is the objective of SVM. So is to find a hyperplane in n dimensions and to distinct classify the data points. So these are called margins. This is called maximum margin between the upper margin and lower margin. So we need to maximize that margin. So the higher the margin, the better the classification. So this is the optimal hyperplane. That's the equal distance between these two planes, x1 and x2, are two margins. So let's see. So this was prepared in the time of COVID. So do you want to enforce social distance? Yes, please. So use SVM to maximize the margin. So our goal is to maximize the margin between two classes. So that's something we're doing in here. So hyperplanes. So this one line is called hyperplane, and this hyperplane is a line in 2 dimensions and a plane in 3 dimensions. So this is somewhere the middle point between this classification and this classification. So hyperplanes are decision boundaries that helps to classify data points. So data points falling on either side of the hyperplane can be attributed to different classes. So if we are introducing a new data point, if it's falling above this data plane, so it just categorizes to red. And if it falls below the hyperplane, it just categorizes into green. So also the dimensions of the hyperplane depend upon the number of features. Yes, so features equals dimensions. So if the number of input features is 2, then it's just a straight line. If more than that, so that would be hyperplane. 3 would be hyperplane. So it becomes difficult to imagine when you exceed 3 features. So it's always difficult to imagine how it would work in 4 dimensions. So here is the support vectors, and this is small margin, and this is large margin, because we have small distance between these two margins and we have large distance between these two margins. So larger the margin, better is the classification. So we will try to find a way to maximize these margins rather than just a small margins. So SVMs are data points that are closer to hyperplane and influence the position and orientation of the hyperplane. So using these SVMs, we maximize the margin of the classifier. Detecting or deleting the support vectors will change the position of the hyperplane. These are the points that help us build our SVMs. It's simple. So the points we need to know is this is the small margin and this is the large margin. So what does these margin means? So is it something like we don't have points after this margin? No, we do have sometimes some points classified out of this margin, but inside this hyperplane. So we do have points, and that's called soft margin. If no points are classified inside the margin, that's called hard margin, which we're going to discuss the next few slides. How can we identify the right hyperplane? So here are the 3 hyperplanes. So we'll just see some of these figures to identify the best hyperplane. So here, if we take the hyperplane A, so some of them are misclassified. And if we take C, some of them are misclassified. But if we take B, everything was classified correctly. So we'll take B as the hyperplane. So when our model tries to build a hyperplane, it just at the first iteration or the first epoch, it just takes some random hyperplane, and then it just makes it orientation in such a way that it finds the optimal number of data points classifying correctly. So that's how the hyperplane was built. So the hyperplane at the first iteration can be anywhere, but it just makes its way to classify all the data points correctly. So that's something about hyperplane. And here we have 3 hyperplanes, and B is the best hyperplane. And if we have this scenario, so every of the hyperplane is identifying the data points correctly. So here maximizing the distance between nearest data points and hyperplane will help to decide the right hyperplane. So from this hyperplane A, so the nearest points are the red, and the nearest point here would be this one. So we need to increase more of the red. So if we go to here, it will increase the distance, and if we go to here, it will be increasing the distance even more. But here we have the less distance. So the optimal point would be C. So we need to maximize the distance between the nearest point and the hyperplane. So that's our aim, to classify the correct hyperplane. So here, maximize the distance between the nearest data point and hyperplane will help us to decide the right hyperplane. This distance is called margin. Yes. So we're going to discuss about margin as well. Identifying the right hyperplane, scenario 3. So if we have this type of hyperplanes, the misclassified hyperplane will give us more distance, but the correctly classified hyperplane will give us correct classifications but less distance between the nearest points. So SVM select the hyperplane with classes that class accurately prior to maximizing margin. So here our priority is to classify rather than having large margins. So SVM decides a hyperplane such that it classifies correctly, and then decides a hyperplane that maximizes the margin. So it just don't maximize the margin first, but it just classifies it first correctly and then maximizes the margin. So this is something important to remember. And can we classify 2 classes? So scenario 4, so we are unable to segregate these 2 classes. So there is no way to segregate this data point here. We just can't make a hyperplane to classify these two classes. So the two classes using a straight line, as one of the stars lies in the class of the outlier. So in this way, in this scenario, we could use other types of hyperplanes, not just a straight line. So this is the use of SVM, that it just don't use the straight lines. It uses other matrices as well, like hyperbola and other equations as well. So find the hyperplane to segregate the classes at scenario 5. So here we could use a circle to classify both of these. Oops. So SVM could use circle. So we can't have a linear hyperplane between these two classes. So there is no way to define these two classes using a straight line. So SVM classify these two. How does the SVM classify these two classes? So this, it solves by the problem by introducing additional feature. So we could just include additional feature in this. So instead of x and y, we could compute one more dimension z to that uses both x and y and get a new feature. We could define the dimension, and it could be easy to define here. So when we look at x and y instead of z, it would be something like this. So we are not taking the equation, circle equation directly, but we are introducing a new feature and then trying to classify it using a straight line. But when we look at the two dimensions, it would be classified something like this. So the is called the kernel trick. The SVM kernel is the function that takes lower dimensional input space and transforms it to higher dimensions. It converts not separatable problem to a separatable problem. So that's what the example is all about. It is mostly useful in nonlinear separation problems. So we'll try to introduce one more feature and try to classify it using a straight line. But again, when we look at the dimensions, it would be something looking like this. So yeah, as we discussed, this is the hard margin and this is the soft margin. So soft margin is something which the data points will be classified inside the margins as well, but there is no way classifying at the decision boundary. But this could be inside the margin as well. But this is the hard margin, so no data points are inside the decision boundaries at the margin. So hard margin. So that's the same matter given here. So we could go through them and read it 3 times. So parameters for SVM. So we have various parameters for SVM as well. So for KNN, we have parameter K, so on. And for SVM, we have various parameters to give the regularization parameter C. We have gamma parameters, kernel, degree, random state, etc. So first, the regularization parameter C. So C parameter is mainly used for penalty parameter of the error term. So you can consider it as the degree of correct classification that the algorithm has met. So controls the trade-off between the classification. So it penalizes the model if it classifies into wrong category. So that's what the regularization term do here in the SVM. So for large C, if we have the large C value, it will be overfitted, and it will be underfitted if we have small c. It's just a straight line. It's not even trying to classify some things correctly, but it's again overfitted. So that's the cons by using large and small c values. So there should be an optimal value to be chosen to classify it correctly. So what happens if it overfits? It won't do in general scenarios. On in real case scenario, if it underfits, it may not perform in training phase as well. But we don't know. It may perform well or may not perform well in testing. And then comes the gamma parameter. So gamma is used when we use the Gaussian RBF kernel. So if we use a linear polynomial kernel, then we don't need to use the gamma. We can just use C parameter. But when we use the Gaussian RBF kernel, we use gamma parameter. It decides how much curvature we should have. So if it's not linear, if it's not a linear problem, we need to have some curves to decide the classification. So gamma parameter decides how much curve we should have to classify them. So if we increase the curve too much, it may misclassify some things. If we decrease the curve too much, it may again fall into the linear problem. So we need to have a optimal value to choose for gamma parameter as well. So high gamma, more curvature, low gamma, less curvature. Yes. So higher gamma, this is the high gamma, only near points are considered. But for low gamma, far points are also considered. So it would be somewhere like this. The distant boundary would be somewhere like this. But for here, it would be here. So we need to choose the optimal value to be considered. So this is again what we discussed. So this is about the kernel. So it's very simple. In this parameter, few options are there. Like if you want the model to be a linear, we go for linear. If we need to have a proper accuracy, we go for non-linear SVM, like RBF, polynomial, or sigmoid functions for better accuracy. So you will see here what different things will look like. So this is the linear kernel. So this is a straight line, and this is a straight line defined to categorize the variables. This RBF kernel, somewhere like this, the circles for the RBF kernel, and this is the sigmoid function or the sigmoid kernel. It's like somewhere like ax square plus bx terms. So this is the sigmoid kernel, a little like parabola, a hyperbola, and this is the polynomial kernel. Okay, we have different curvatures here instead of the same curvature. So we could actually define the RBF kernels as we wish, and that's where the kernel parameter is used. So it again classifies whether the classification problem is a straight line or a curvature or a circle or anything. So degree, next thing would be degree. It controls the flexibility of the decision boundary. So higher degree, more flexible, but highly recommended for polynomial kernels. So if you see the gamma, you could see like different uh, plots for different gamma values. So you could see if we have more of a value, it's overfitting, and if we have too much less value, like 0.1 or 0.05 or something like that, it would not classify. It may underfit. So this is one thing about gamma. It just it's a parameter to consider. So we could actually see these graphs when we code to to make an optimal decision on on these values. So when we build SVM, we just categorize or we just make graphs so that we understand what was happening and what are the optimal parameters we need to choose. And it again depends on the data we are using. It again depends on the classification task we are using. For example, if you are working for a gaming company, you could classify you could misclassify something. It doesn't matter too much, but if you're working in medical field, you need to classify it more accurately. So that's somewhere something where we need to consider the hyperparameters uh, to choose from. Again, it again depends on the data, the problem you're uh, facing, and everything. So SVM summary. So plot the features. So we consider the margins. So these are the margins. This is the hyperplane. So it won't classify. It's not the correct hyperplane because we could even classify this thing. So margin is not important, but classification is most important. Then we think about the margin, and we draw hyperplanes randomly. Oh, this goes yeah again. So at first we take a random hyperplanes, and then we choose a hyperplane that classifies correctly, and then we consider the margin. So if a new data point is introduced, it again changes the hyperplane to here to classify it correctly. Or if a straight line is not possible, we'll just use the curvatures as well based on the problem we have, and we could choose these optimal values based on the parameters we choose. So application simple. It's used in handwriting recognition. So it recognizes the patterns, good, and face detection, We use SVMs for face detection as well, text and hypertext categorization, image classification, bioinformatics, protein classification, and cancer classification. Pros: more effective for high dimensional space, not suitable for large data set. So these are some of the pros and cons we could go. So more effective for higher dimension space. So we could actually use this classification technique for for more dimensions, right? So we could actually use the curvatures instead of straight lines. So it's more useful or works well on unstructured, semi-structured data and handles nonlinear data. Yes. So SVM has L2 regularization features, so it has good generalization capabilities and prevents it from overfitting. A small change in the data does not greatly affect the hyperplane, so it 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 is prone to uh, large changes. So cons are not suitable for large data sets. So we need a more computational power to make it suitable for large data sets. So it's not always feasible to choose this type of classification for large data sets. Sensitive to outliers, hyperparameter like cost and gamma is not easy to fine tune. We need to take a lot of decisions to make sure we are choosing the correct hyperparameters, because it's not always easy to choose hyperparameters in this case or in this scenario. So it takes long training time on large data sets. Yes, that's what we discussed. It's not suitable for long data sets. Sometimes it may take days to train the data sets, sometimes using SVM. SVM model is difficult to understand and interpret by human beings, unlike decision trees. One must do feature scaling of variables before applying SVM. So here we have normalization, scaling, collinearity, and outliers. So we have different models and we have different parameters and we have the highlights which you can go every time. So again, it's this slide again to choose accuracy precisions. So we'll categorize or we'll find the hyperparameters based on the classification we are getting when we finish the model. So if we have like higher accuracy, we choose that particular parameter and we use those parameters in the real-time scenarios. So how do we calculate different uh, matrices? So here is the table. So if both are true, I mean the actual is true and the predicted is true, it's called true positive. If the actual is negative, predicted is positive, it's called false positive, false negative, and true negative, and so on. So we calculate the accuracy based on the number of data points that are classified correctly. So here they are classified correctly. So TP plus TN by total number of classifications would give us accuracy, precision, something like a true positive. How many true positives we got? Recall would be like, we have multiple matrices. So here, when we choose a model, sometimes we need to choose the model that gives higher accuracy. Sometimes we have this thing to choose higher precision and so on. It again depends on the matrix you are using. You could use any matrix matrices to choose the best hyperparameters. It again depends on the problem statement you have. Now, is the example. It's one of the example. So breast cancer Wisconsin's data set. So number of instances 569, 30 numeric. So this is the attribute information, and the class would be having the cancer or not. So using different regressions, for example, logistic regression, we got the accuracy of 97. So to understand this, support means the number of data points, and this is the F1 score. How balanced is your data set? This is the recall precision. This is the accuracy, and you need to understand in this way. Categorizing into 0 means uh, not a cancer and having a cancer. And these are some of these techniques we have discussed till now. We can see what are the accuracies we got on different matrices or different classification techniques we discussed today: 94, 97, 96, and 94. Again, it's not always useful to focus on accuracy. Sometimes we need to classify them correctly rather than classifying it. I mean, classify the true positives rather than classifying them correctly on the classes. So it again depends on your problem statements. And again, this accuracies may vary if you vary the hyperparameters we discussed till now. So again, there are a lot of hyperparameters on SVM. So we need to choose a lot of hyperparameters. You can visualize the graphs to choose the best hyperparameters, and the performance can even be better or even become worse using the same model but different hyperparameters. So that's something to remember. And yes, that's the end of classification part 2. Any questions?